everyone, welcome back to The Explainer. Today we're diving into what are quark generations, which is part 2 of our deep dive into what are quarks. We're going to unpack some serious geometric mysteries today, treating this just like a high-level physics paper presentation. We'll be breaking down some pretty complex quantum mechanics into a very clear visual logic flow. So if you've ever wondered why the absolute fundamental building blocks of our universe are structured the way they are, you are in exactly the right place. Here is how we're breaking down today's scientific deduction. First, we'll look at the quark flavor problem, then strange quark decay patterns, antiparticles in our space, the generation mechanism, and we'll wrap it all up by simulating quark masses. All right, let's jump straight into section 1, the quark flavor problem. Looking at the standard model layout, we know the 6 quark flavors are neatly organized into 3 distinct generations, right? And each generation perfectly pairs an up-type quark, which carries a positive 2/3 charge, with a down-type quark, carrying a negative 1/3 charge. Generation 1 holds our common up and down quarks, the stuff making up normal everyday matter. Then generations 2 and 3 contain the much heavier, strange, charm, bottom, and top quarks. And, as you know, those heavy hitters typically only pop up in extreme, high-energy environments, like cosmic rays or inside particle accelerators. But here is where things get super weird. Look at this glaring anomaly in the data. When we map out the natural log of these quark masses, we see that as the generations increase, the mass doesn't just tick up a little bit. It skyrockets exponentially in this very specific, distinct stair-step pattern. In physics, this mystery, why quark masses are so widely and bizarrely scattered, is known as the flavor problem. It is honestly one of the greatest, most frustrating puzzles of the entire standard model. So, how do we solve it? Well, that brings us to section 2, strange quark decay patterns. Instead of just guessing, let's look at how these particles actually break down in reality. By tabulating these primary decay formulas directly from our source data, we can deduce a totally fascinating rule hiding in plain sight. Look closely at the patterns here. Up-type quarks, like charm and top, almost always decay into down-type quarks of their exact same generation. It's very predictable. But down-type quarks, like strange and bottom, they actually cross generational lines, decaying into lighter up-type quarks. You can see this zigzag pattern crystal clear with the solid arrows here, visualizing those high-probability decay pathways across the generations. The pattern is undeniable. But to truly crack the code on the architecture of these generations, we need to zoom way in on the strange quark specifically. We need to uncover its hidden internal structure. Let's break down the strange quark's most revealing decay path. A strange quark very frequently breaks down into an up quark and a W- boson. Now, depending on the parent hadron, that W- boson has a massive probability of decaying into a pion. Mathematically, that pion is made of a down quark and an anti-up quark. Think about what this actually means, because the strange quark's breakdown literally yields an up, an anti-up, and a down component. Logically, the strange quark must inherently contain those 3 exact flavor components bundled up inside its own structure. Mind-blowing, right? Which leads us perfectly into section 3, antiparticles in our space. Now, in our space theory, particles are definitely not just abstract little dots. They are rotation vectors. They are basically vortices of angular momentum. And an antiparticle is quite literally just a mirrored rotation vector. When you mirror that vector, the direction of rotation reverses, and as the wave equations show us, reversing the direction of this geometric rotation is mathematically identical to reversing the phase of time itself. And this right here brilliantly visualizes the exact deduction we just made. If the strange quark really is built from an up, an anti-up, and a down rotation, look at the geometry. That up rotation and the mirrored anti-up rotation perfectly cancel each other out in terms of their outward properties. So what's left over? Only the down properties are visible. This is a huge revelation. It completely explains why the strange quark behaves exactly as a down-type quark on the outside, even though it's secretly carrying all this highly complex, hidden internal structure. All right, let's keep building on this in section 4, the generation mechanism. So how do we get the heavier generations? Well, in this model, quarks are generated by sequentially stacking color rotations, kind of like adding distinct layers of vibrational energy. Give an up quark 1 rotation, stack a second one on, bam, it becomes a down quark. But for the strange quark, simply adding a 3rd rotation isn't enough. Because these quarks are existing outside of a stable 3-part baryon structure during this transition, adding a simple 3rd rotation creates a highly unstable up-like state. To soak up that excess energy and stabilize, the strange quark specifically requires adding both a color rotation and an anti-color rotation. That is the exact mechanism that injects those anti-properties we were just analyzing. This flowchart maps out that exact stacking process perfectly. As we keep stacking these rotations, moving from strange up to charm, charm to bottom, we eventually slam into a hard theoretical boundary, the up-like limit. A down component can mathematically become up-like with added rotation, but there is simply no state higher than up-like. Once a component hits this absolute ceiling, any further generational energy forces massive structural shifts, causing properties to either cycle back or require even more complex internal cancellations. This stacking limit is the literal blueprint for why quark generations exist. Which brings us to our final stop, Section 5, Simulating Quark Masses. Let's put this geometric model to the test. Here is our initial R-space simulation. Just by doubling the required energy for each rotational state change, the simulation successfully captures that general upward stair-step trend. You can clearly see how adding the anti-rotation for the strange quark and hitting those U-like limits for the heavier quarks creates these specific steps. But as a rigorous explainer, we have to acknowledge the elephant in the room. The simulated mass increase is still significantly smaller in magnitude than the actual observed reality. It's just not enough on its own. But hang on, because this is where the whole thing clicks into place. When we apply a crucial correction factor, specifically accounting for the absolutely immense kinetic energy generated by the quark's orbital revolution inside the hadron, everything changes. By taking that base rotational energy and raising it to the power of the state changes to represent this revolutionary speed and radius, our simulation scales exponentially. Look at that comparison. The simulated data now aligns remarkably well with the actual observed mass logs. It's incredibly strong evidence that generation masses are dictated entirely by geometric state changes combined with revolutionary kinetic energy. We've literally, mathematically connected the dots from a weird decay anomaly all the way to a geometric mass simulation. But it leaves us with a totally provocative final question to wrap up this explainer. If geometric rotation and orbital revolution dictate mass this flawlessly, what other quantum secrets are just waiting to be discovered if we can refine the exact mathematical rules of this internal revolutionary motion? Think about it. Thanks so much for joining me to explore the hidden geometry of our universe today. Catch you next time.